All right, so last class was pretty fun. We got to look at chapter 6, and I brought something to swing,
What?
work on this centripetal acceleration.
You said you brought something in?
Yeah, I should have brought it.
Today,
Today.
for the
Today.
lab.
Well,
Yeah, it's lab. It's our lab day too.
What you know?
Y'all gotta come to class.
All right, man.
I missed one class.
It was just like a Halloween type of a axe.
Okay.
Yeah, just
Okay.
but it was just to show the centripetal acceleration of like swinging a bat or a golf club or something. So as we talk about rotation angles, the centripetal acceleration, centripetal force, Coriolis, it's good to know that you can apply it to swinging a golf club, you can apply it to swinging a bat, you can apply it to if you have your car drifting or something, like having the angular motion. So I did bring one thing that I used and something to show the centripetal acceleration. So a lot of times you'll see somebody like swinging an object on a rope, you know, a ball or whatever.
Hypnosis.
Yeah. So and there you can see we were talking about the angular velocity, the linear velocity, centripetal acceleration, that ratio of centripetal acceleration to gravity. And then we talked about Coriolis, translational, like things spinning when things are spinning. That had to do with the perspective, looking at an object in motion, like dilation or perspective, frame of reference was that name of it. So a frame of reference. So, hey, great day. Hey, great day, Mr. Erica. Great day, Mr. Treasure. So last class we talked about chapter 6. So we're looking at rotation angle. So the change in theta, ds over r, the radius. So and then it looks a lot like that. The radius where there's an angle, and then ds is the change in that angle going around. So this talks about the CD player. You know, it's another circular motion. So it's uniform circular motion, gravitation, angular velocity, a car's tire spinning. You know, that's another angular velocity equation, or even a disc or the. Yeah, I don't know why they. Yeah, they had a fly. Yeah. See, this was the take-home experiment. Tie an object to the end of a string, swing it around a horizontal circle above your head, swing at your wrist. Maintain uniform speed as the object swings and measure the angular velocity of the motion. What is the approximate speed of the object? Identify a point close to your hand and take appropriate measurements to calculate the linear speed at this point. Identify other circular motions and measure their angular velocities. So I'll go through a little bit more so you can understand why they are telling us these things. So you have centripetal acceleration. So at each point on the circle, there's a velocity that we're going to be moving. So a lot of times, say NASA, there may be a motion that we would like to test on the body as if we're going in outer space. So of course those velocities need to be tested, and going around in a circle is something that can increase your gravitational pull. Well, you're increasing your acceleration, and then it may be going greater than gravity. So as centripetal acceleration increases, you're going into centripetal acceleration, brings you closer into the center of the object that's spinning, and the Coriolis, it is Coriolis, is the opposite of that, which they call fictitious forces, non-inertial frames. So we have these equations: centripetal acceleration equals v squared over r, where v squared over r, where omega is included, which omega is d theta over dt. So this is something like, how does the centripetal acceleration of a car around a curve compare with that due to gravity? So you can see with a car moving 25 meters per second, going around a curve with a radius 500 meters and a speed. So then you could, with just the speed and the radius of what they're going, you can find out the centripetal acceleration. And then they ask, well, compare this to the acceleration due to gravity. So then you're taking a ratio. Well, at this speed, 0.128 of gravity is the acceleration, centripetal acceleration that you're moving in. So then we start looking at the car, and we were talking about, okay, so if I'm moving around this curve, the car wants to, since you're turning your tires, it wants to go around this curve. But then there's also a force that leads you out, and we'll talk about that too. Because I'm sure you've experienced when you're in a car and you turn real fast and then you go the other way. So that's Coriolis, or the centrifugal force. You said alignment.
I mean, if you go that way, you might need a wheel alignment.
Oh, yeah. So not the cars. The car's angle is in the right direction, but you have a rebound effect, which is where centrifuge got its name from centrifugal force. So we were talking about centrifuges before and how they increase the speed so that the particles are moving. So that's the centrifuge. How big is the centripetal acceleration in an ultracentrifuge? So in an ultracentrifuge, we saw centripetal acceleration is for this one 472,000 times as strong as gravity. You know, so that is very intense. An ultracentrifuge. We did that Ladybug. Calculate the coefficient of friction on a car tire. Calculate ideal speed and angle of a car on a turn. So you're just putting in F equals ma, but then we notice centripetal acceleration is v squared over r. So and then centripetal force is mr omega squared. Since we know centripetal acceleration is also r omega squared, which is right here. And then if you're solving for r, if you're trying to understand what the radius is, then v squared over the force, centripetal force. So those are some of those What coefficient of friction do car tires need on a flat curve? Calculate the centripetal force exerted on a 900 kilogram car that negotiates a 500 meter radius curve at 25 meters per second. And then we start talking about the coefficient of friction, where certain tires are going to give you a certain friction. You know, if you have a greater tread, then that's going to give you a greater coefficient of friction. If you have water in your vicinity, water mixed with oil, we talked about before, water mixed with oil is one of the worst places, brings down the friction. So calculating the centripetal force, negotiating this type of curve, mv squared over r is what we want to look at. Since they said force, centripetal force, we're looking for this equation, mv squared over r. So we put our mass of the car, the velocity squared, the radius. Strategy for B was talking about the coefficient of friction. So and then we're adding in, I don't think that we've talked about mu. Did we talk about mu? No, we did. Yeah, so mu is the static coefficient of friction. So now we're adding in another term, another variable, mu, because we got to look at the coefficient of friction. And then N, we know that's the normal force. So we have everything all right?
It is not. We're going to stop you right here today. We just want to talk about the way class is going, per se. We just think this method isn't working. Let's not all speak at once. So we just but seriously, we just
It's too much talking.
It's too much talking. There we go.
Yeah, then we need more problems.
Okay.
Okay.
That's it. That's all we need is more problems.
We
We don't
really,
have to be up here talking to us.
Honestly, if you just want to skim through, if you know the gist
Yeah,
of
like if we
it,
have, I feel
and we
like
just see the problem, that way it cuts this reading down, because I'm not getting with this reading at all. Like, I'm doing something else in the between time while you read it. But when you do these problems, I just be so ready. So
Yeah.
I see the problem.
Yeah, I just wanted to make sure that we know what we're about to do. But yeah, that's we were about to solve for these things. Wanted to see what y'all's swing looks like.
okay, I feel like another thing, I don't know, but they probably gonna have something to say, but I think everybody should be.
Just the
working on board.
disclaimer. This is not like shots at you or anything. This is just like our learning styles are different. You know what I'm saying?
It's not a problem.
You know, we're just trying to, we want to max out this experience of this class. You know what I'm saying? Because we need, a lot of us want to be physicians, and we need this class. You feel what I'm saying? So we want to actually understand what we're doing. Like it's not like a bird class, whatever. We just want to get through. We want to understand what this is.
Yeah, that's cool. I know a lot of times the like for me, understanding like the big picture is like one of the big things about physics and whatnot. And so that's why I know the lecture or, talking about what all is going on, like really helps. Yeah, we can definitely.
Or even if
Like I was saying,
asking us what we know and what we don't know.
Yeah, that's what I
You
was
know what I'm
saying.
saying?
Like, we could work out problems on the board, or put like, I don't know, just work out problems on the board, like
Yeah, that's cool.
knowns and unknowns, stuff like that. On the board, we do that ourselves.
Yeah, that's cool. Yeah. Right, J-Mac was just like,
And she was like built up, but
it's
she
cool.
was like,
That's cool. Yeah, we can do that.
let's look it out.
Do you have like any worksheets, that you could, like based on the chapter, like next week probably we're starting chapter 7, so maybe have some worksheets printed out for us. The expectation is that we all read the chapter anyway, so by the time we get to class, we got some worksheets flowing, and you can look over them, or we can just go over them as a class.
Yeah, that's a bet. Yeah, we can do that. I'll write that down. Yeah, yeah, we could go over the problems. That'll help out. And then I'll write down what the best questions are.
And so today, what did you do? 6 and part of 7? To get where we need to be, how much do we need to get done? Because I know that's what you were saying today.
Oh, yeah, I was just chapter 6 and 7 exercises. Yeah, so let's see here. What are the best questions? So getting closer to 7, I mean, as much of 7 would be nice because we'll have our homework for 7. I mean, if we're not able to get through some of them, we could, I mean, the main thing is the online, homework.
I just want to make sure, we're on schedule with where we need to be, like you said. Instead of, being behind and we're trying to make it happen.
Yeah, the main thing is the homework,
According to this, we need to be done, 7.7 halfway done, right?
yeah, but I'll probably have to have this due next week. I mean, unless we just work on it and then I could leave it.
Whatever you feel, whatever you feel is best,
You don't even have to do next Sunday. Maybe like Tuesday we'll come to class on 15.
Yeah, I could leave it open. I mean, you could always go back, or not always, but you could go back and increase your grade as we go forward. But let's check out. Alright, let's see if there's another support. Class recordings. So then we have discussion 3. Problem set 3. Cool, so we could work on those. We could possibly see what we could do here. And then also, see what I really wanted to do to kind of help with that, since most of us didn't get to complete what we did last class. So let me pull up some of the equations. Yeah, so I know conceptual questions might help give an overall, but the problems and exercises, yeah, we can do that. Here, I'll go to what we did last class and see if y'all would like to track your, we could solve for how fast you swing as well. So these are some of the like equations and some of the things that we did last class. So I'm thinking, so what I planned on doing was like taking turns doing like swinging like a, you know, a golf club, a bat or something, you know, taking turns to see how much of a speed that we have. So that was something that'll help us to understand angular velocity. So that was something that I had in mind. Or we can see what the problems look like. Wait, y'all want to try that? All right. But what we did last class was like swing it, and then we saw like where each point where we made a full turn. So like our 2 pi is like 1 revolution, which is 360 degrees. So I asked Miss Erica, please start the stopwatch here, and then we spun it around and then stopped, and we got to see the speed. So that's the speed of 1 revolution. So I had 7.66 revolutions per second while just doing this. And then the linear velocity, because each point you have a linear velocity too. So that's where that linear velocity is. So, and then that's r omega, so the radius, and then omega is what we just got, the angular velocity. So, and then that was 3.37 meters per second going around. And then centripetal acceleration, v squared over r, 25.8, because we got the radius of what this is 0.44 meters. And then ratio to gravity, that's 2.63. So I was going 2 times faster than what the gravity, which makes sense because, you know, gravity's gonna want to pull it down. But then as I'm increasing speed, you know, I'm overtaking that force of gravity. So 2.63 faster than gravity. So that was for the carpet. This is just showing the frame of reference, looking at a car tire spinning. And then the Coriolis force, which is similar to centrifugal force, which is just, there's a force coming in, force going out. So let me go ahead. As you turn, you start going to the right. I'll leave that up since it has the equations. Go ahead and duplicate this so we can have the equations there. Rotation angle and angular velocity. Semi-trailer trucks have an odometer on one hub of a trailer wheel. The hub is weighted so that it does not rotate, but it contains gears to count the number of wheel revolutions. It then calculates the distance traveled. If the wheel has a 1.15 meter diameter and goes through 200,000 rotations, how many kilometers should the odometer read? Calculates. Alright, so should have our revolutions. So it looks like we have.
Revolutions would be the oh, I'm sorry, I didn't cut you off.
Nah, that's cool. Looks like we have our. Looks like we have our radius. I wonder how I could. Well. So I could erase this. It's so hard. So we're looking at
Semi-truck.
truck. We have an odometer reading. Which is our RPMs. So we have a 1 point. Here. Diameter. Alright. And then we have goes through 200,000 rotations.
So rotations are different from revolutions?
That's the same thing.
Oh, okay.
Yeah, yeah, it's gonna be the same.
Okay,
So I'll say the revolutions. How many kilometers should the odometer be? Kilometers traveled. So we have our angular velocity, v squared over r. Alright, let's check out our equation. So we want to get our distance. And then I could find a distance with the amount of time.
Do we need to try to get time? Then try to get time?
I think that our that's what I was planning.
So we're using this equation, this formula.
I'm looking at